Just when you thought all this nonsense with ions was over. First, we learned about simple binary ionic compounds, then we learned about compounds involving transition metals for our ionic compounds. Now we have these things called polyatomic ions. Oh my goodness, when does it ever end? By the end of this video, you should be able to utilize the steps and the rules to name all types of ionic compounds, including now those that contain polyatomic ions. But before we get into what the heck a polyatomic ion even is, I have a question for you. Even if you're not a renowned baker, most of us know that flour is a key ingredient to bake most types of cookies, including my personal favorites, chocolate chip Cookie Monster. So if flour is a key ingredient and pretty much dominates all the other ingredients in a recipe for cookies, why don't we just call cookies flours instead? Hopefully you're thinking about all the other ingredients that make cookies cookies. You're thinking of the eggs and the loads of sugar, I might add, the vanilla, the chocolate chips. What are chocolate chip cookies without the chocolate chips? Nothing. Absolutely nothing. So why don't we just call them flours? Because just having flour as our ingredient wouldn't give us cookies. And if we only mixed flour and eggs and X-nayed the sugar, if we X-nayed the vanilla, if we X-nayed the chocolate chips.
Oh no!
Gasp! Blasphemous. No, don't X-nay the chocolate chips. We still couldn't call it cookies because it would just be flours and eggs, essentially bread. Like, we can't call it flours. That doesn't make cookies yet. So what I want you to get out of this is that there's many parts to make a whole. It requires many things in a recipe to make a full chocolate chip cookie. More than just one piece, one ingredient will create the recipe that we all know and love so dearly. Likewise, polyatomic ions, poly means many and atomic means atoms. There are many atoms together, just like in the ingredients for a recipe for cookies, there are many ingredients together. Here, there are many atoms together that form a single ion. So overall, polyatomic ions contain several nonmetal atoms bonded together, but they have an overall charge. So those nonmetal atoms will stick together, like we learned in the past, covalently bonded nonmetal atoms. But these covalently bonded nonmetal atoms have an overall single charge to them. Weird. So it's covalently bonded nonmetal atoms, but it's an ion and it bonds ionically because it has a charge. So for example, NO2 is a polyatomic ion called nitrite. Notice that N and O are both nonmetal atoms, and I like to think of it as an Oreo cookie. So an Oreo cookie has two chocolate pieces. That's kind of like your two oxygen atoms present, and it has the nice creamy vanilla center. That's kind of like your N atom present. So we have NO2. We have the one filling of N and the two oxygens for the cookies. This whole cookie itself has a -1 charge. So it's bonded together, NO2, but the whole cookie has a -1 charge. There's not one particular atom in there that has the charge. So what we want to think about here is that the entire cookie moves as a unit. We're not going to split the cookie up. We're going to keep the cookie whole. There are lots of polyatomic ions, and I hope you don't have to memorize these for your sake, but you should become familiar with them and how to identify them if they happen to be present. Polyatomic ions all have special and unique names. And the good news here is that you'll always know that you're dealing with a polyatomic ion if it happens to end in ate or ite. I like to remember this in a little ditty. Here it goes. If it ends in ate, it's a polyatomic ion. If it ends in ite, it's a polyatomic ion. But sometimes an ide is a polyatomic ion. But always the ate and the ite are polyatomic ions. You're welcome. I'm sure that'll be stuck in your head for the rest of today. So again, notice the names behind me in the image, and you'll see that a lot of these names end in ite or ate. You know they have to be polyatomic ions because they end in ite or ate. The bad news here is that some of them look really similar. So the names look really close, but the chemicals are entirely different. For example, we have nitrate and nitrite right up here. Nitrate has an extra oxygen. Nitrite has only 2 oxygens. That's a huge chemical difference. So don't get those two confused. Be diligent in looking at the ends of ate or ite. So nitrite, like a little tiny bit, kind of sounds cute, like ite, nitrite. And the nitrates are like nitrate, they ate too much. In this case, nitrate, nitrite. Nitrate has too many oxygens, it ate too many oxygens. And nitrate is missing an oxygen, so it has less of that atom. I know that's really a corny way to keep it straight, but that always worked for me, so I hope it works for you. So although there are all of those polyatomic ions from the previous slide, I have found personally that these are the ones that pop up most often. So these are the ones you should probably write down and familiarize yourself with the most. Notice that all of these end in ate or ite with a few exceptions. There is hydroxide, there is cyanide, so sometimes an ide is a polyatomic ion. And check it out, there's one above my head, ammonium, that's super special and doesn't end in anything we've seen thus far. But it's also special because it's the only +1 polyatomic. More on that here soon. So as I mentioned before, what kind of atoms make up polyatomic ions? When we think of our nitrate and nitrite, that was our N and our O. We also have hydroxide. Hydroxide is O and H. We have sulfate. Sulfate is S and O. We have a lot of things that are coming from the non-metal range of our periodic table. So basically what I'm getting at here is that polyatomic ions are non-metal atoms bonded together in a group, but they have a charge. So we have a group of covalently bonded atoms that are held together via covalent bonds, but overall has a charge. So therefore it is ionic and can form an ionic bond with a metal. Or in the case of ammonium, the one behind me, can form a bond with another nonmetal and still be considered an ionic bond because it's a polyatomic ion. Now you might be wondering to yourself, how is it that we even have a charge on something that's covalently bonded? The whole point for having the covalently bondedness, if you will, was so that each atom fulfilled the other's octet. How is it that we come about having an ion, i.e. an area where there's more or less electrons, on something that's supposed to be completing each other? The charge that is on a polyatomic ion is due to the overall excess or shortage of electrons. So in other words, there was a gain or a loss of electrons somewhere from an already happy molecule that once was. And the result is then a polyatomic ion that is coping with life by having a charge and then needs to find something else that has the opposite charge in order to balance itself and regain equilibrium, if you will. So for example, ammonium, NH4+1, the one that's behind me, should have a total of, well, 4 hydrogens, so there's 1 electron per hydrogen, and 5 electrons coming from the 1 nitrogen. So we have 5 valence electrons from nitrogen, 4 valence electrons from hydrogen. Really, we should have 9 total electrons. But if you look at the image behind me and you count up all those dots, you see that there's only 8. So the lack of having that extra electron actually makes ammonium more positive. So the lack of that extra electron for 9 total, instead only having 8 intrinsically negative things, since we're missing 1 more intrinsically negative thing, we end up with an overall Oreo cookie that is positive. Ammonium ends up with an overall +1 charge due to the lack of the extra electron it's missing. Yeah, that's great and all, Duckonta, but how does that even come to be? This is one of those things that's best explained with a little bit of organic chemistry. Now hang tight. This is one of those things that's a little easier to explain with a reaction sequence. So bear with me here. I'm going to show you how a polyatomic ion is formed using water as our example. So if you look over there, that glass full of water, notice that I've put in a lot of water molecules. There's not just one water molecule floating around in your glass of water when you drink it. There's thousands upon thousands of them. They're all interconnected and bonded together via hydrogen bonds. And all of those thousands of hydrogen bonds between all of the water molecules in your glass of water is what gives water all of the physical properties that we know and love. One of the things that is not commonly known about water is that it actually exists in this equilibrium shift back and forth. So I'm going to show you a reaction between water and itself. Now, if we have a pure glass of water, nothing else in it, just water molecules, they're actually reacting with themselves. The water molecules are exchanging hydrogens, exchanging electrons. They're moving stuff around and shifting back and forth. This is normal and natural, but they exist in equilibrium, meaning there's an equal balance of both sides of this tug of war. And that's why we can still call it water. It's not necessarily going to like kill us because now it's something different, but there's an equal amount of each side of water changing that it's still water. So let me show you what I'm talking about here. So if water were to react with water, let me show you what that looks like with chemical models. All right, we have two water molecules ready to react with each other. Notice I have also drawn them as bent because water is never linear, it's bent in shape thanks to those lone pairs of electrons on the oxygen in the middle. Let's see what would happen if these two were to react with each other. What can happen is that the electrons on oxygen, the lone pair, can suddenly decide, hey, that hydrogen on the other water is looking pretty foxy. I like the way that that hydrogen dressed up tonight. I'm going to steal it from that other water molecule. So this water molecule is literally going to reach out and steal this hydrogen, rip it off of the other one. What happens then is that water molecule number 2 has essentially stolen a hydrogen off of water molecule number 1. Now don't forget that in each one of these bonds lives 2 electrons. So if water molecule number 2 is stealing the H off of water molecule number 1, those 2 electrons have to go somewhere. And those 2 electrons are going to go towards the more electronegative atom that they happen to be right next to. So they're going to jump over onto oxygen as their safe home. That's where they want to be now. They've got to go somewhere. They can't just poof, disappear. So then what we end up with is this OH molecule missing that hydrogen, but has that little extra pair of electrons on the oxygen now that it didn't have before. And because you have that little extra pair of electrons there, the O gains a full negative charge. It becomes ionic. And now we call that hydroxide. Well, what about the other guy? The other guy gained a hydrogen. So now that one is O, still has these 2 H's on it, but now there's a bond where those lone pair of electrons used to be, and a stolen hydrogen. So essentially what we have now is a molecule of hydronium where we've removed the lone pair that was keeping the whole thing neutral to begin with. And since we removed negativity by removing a lone pair and putting it into a bond, we now have an ion that's positively charged, a cation. And that's called hydronium. So as I mentioned, this happens with water all the time. If you're drinking a glass of water right now, this is happening in that glass of water as we speak. Now, what did I mean by equilibrium? Equilibrium means that it can shift back and forth. That's what these arrows mean. It can go back and forth, this reaction that is. Meaning that, well, there's a positive and a negative, and hydronium ion has an extra hydrogen, and hydroxide really would like a hydrogen since it's got a full negative on it. So there's nothing stopping this pair of electrons now coming over and stealing this H off of hydronium. And then you'd end up with 2 water molecules again for the whole process to happen all over again. So this is just one way that you can create a polyatomic ion, where you have covalently bonded atoms with an overall charge, making it either a cation or an anion. And then we call it a polyatomic ion. All right, so what are the steps then to go from the name of something containing a polyatomic ion to the formula? How do we write the formula out? First things first, you need to take note of whether or not there's a polyatomic ion present to begin with. And the way we do that is checking the anion, or the second chemical, most of the time, unless it's ammonium, which that would be the first chemical, but that's an exception. And if it ends in 888, or if it ends in ite, then it's a polyatomic ion. Or sometimes an ide can be a polyatomic ion, like hydroxide. But hopefully you recognize hydrox means poly, many, atomic, atoms. So hyd is hydrogen and ox is oxygen. So if the name sounds like there's more than one atom present, then it's probably a polyatomic ion. So for example, we're going to look at potassium chromate through these steps. Step 2 is to write the cation's elemental symbol with its respective charge, whatever that may be. In this case, for potassium chromate, potassium is K, and from the periodic table, it's +1 charge. Step 3 would then be to write out the polyatomic ions symbol, so the overall symbol, with its respective charge. You're going to have to look back at the polyatomics that you wrote down, or make sure that you look up what the polyatomic is. In this case, we're looking for chromate, and we see that chromate was right there in our list. Cr04 -2. So that -2 applies to this whole cookie. Now remember, the whole cookie is literally Cr with 4 oxygens around it. And that whole cookie is -2 charged. The whole thing is charged -2. So it's a smart habit to start putting parentheses around your polyatomic ions to keep them together. And step 4 from going from the name to the formula with a polyatomic ion is to use the drop and swap method, just as we had before, in order to balance all of the charges to 0 overall. So potassium chromate, there's a picture right there for you. It's nice and yellow. Check out all of those lovely OSHA labels. Warning. If you don't know what those OSHA labels mean, be sure to check out my previous video on identifying safety hazards from chemical labels. So now all we have to do is that drop and swap. I put the parentheses here just to reinforce to you that when we do drop and swap, we're dropping on the outside of the parentheses, not the inside. If I do the inside, then I change the polyatomic ion itself. We don't want to do that. We want to change the number of cookies that we're adding, so whole units. Don't change the actual cookie itself. So here we'll take the 1, drop it down on the outside, and here we'll take the 2 and drop it at the bottom of the K. So what we end up with is K2 Cr04 with a 1 at the bottom. Again, if there's a 1, we don't need to show it. But it is still a good idea to start putting your polyatomics in parentheses so that if there were a number on the outside, it would stay on the outside. For example, if I didn't have those parentheses and I wrote K2Cr041, that sure looks like I've got 41 oxygens. That is definitely not the same thing as this. Big no-no. All right, let's give these a try and see if we can figure out how to get from the name to the formula with polyatomic ions in them. Beware the ite versus ate. The confusion between the two because they are so similar. When you're looking at your list, make sure you are picking the correct polyatomic ion that goes with the name. On your marks, get set, and pause the video so that you can try these first. All right, we've got sodium, which is Na. We're going to write the charge. We're going to write the symbol for the cation and its charge first, so Na +1. Nitrate is NO2 -1. Now that -1 again applies to the entire cookie, the entire polyatomic. In this case, we don't even have to drop and swap because we have 1 - 1 gives us 0. So our final answer is simply NaNO2. So then what about sodium nitrate? He ate a little bit too much. That's going to be Na, again, sodium, +1. And nitrate has the extra oxygen. That'll be NO3 instead of NO2. And it also has a -1 charge for the whole cookie. This is the same as before where 1 - 1 gives us 0, so that's pretty convenient. We don't even have to drop and swap for this one. Our final answer is simply NaNO3. All right, for calcium, that's Ca. And calcium has a +2 charge. And there's also carbonate. 8 tells us that it's a polyatomic ion. If we look over at our list, we'll see that carbonate is CO3 -2. Conveniently, 2 - 2 gives us 0, so we don't have to drop and swap here either. Our final answer would just be CaCO2. 3. Now this last one, however, we are going to have to drop and swap. So let's check it out. We've got calcium plus 2, and bicarbonate is HCO3 minus 1. So this one, we do want to make sure we put our polyatomic ion in parentheses so that we can drop and swap correctly. Now when we drop and swap, we're going to have this 2 go down here at the bottom of the parenthesis, and this 1 go down here at the bottom of the calcium. We end up with Ca1 parenthesis HCO3 with the 2 on the outside. This essentially means that we have 2 bicarbonate polyatomics. We have 2 bicarbonate cookies. Now you might not be familiar with calcium bicarbonate, but you should be pretty familiar with sodium bicarbonate. That's baking soda. Also, the antacid tablets above my head, those are your calcium carbonate. They help neutralize the pH in your stomach and hopefully not give you acid reflux. Think you've got it? Go ahead and test yourself before you wreck yourself as the final wrap up for this video, and try and write out the neutral molecular formula for the following molecules containing these polyatomic ions: magnesium sulfate, calcium chlorate, lithium phosphate, and beryllium acetate. As a random side note, magnesium sulfate is something that can help suppress preterm labor, preterm birth. So help stop a woman going into preterm labor. Kind of cool. Polyatomic ions are pretty useful. If you'd like the answer for these test yourself questions, please say so in the comments below, and I'll be happy to upload a video giving you the answers to these questions. Give me a quacks up and hope your day is just ducky.
No ducks, no glory.